Calculus, at least the concepts developed from calculus, are used all the time in civil engineering. Anytime there is a rate of change of something, then the derivative is an efficient way to characterize it, and anytime there is an area under some function describing behavior, then the integral is an efficient way to quantify it. Today, we'll be looking at bending moment and beam deflection in cantilever beams, and how integration and differentiation is used in these. The cantilever beam is one with one end completely fixed so that it cannot move. Furthermore, it's classified as delta equals 1/3 times PL cubed over EI, and I being width times h cubed over 12, E being Young's modulus. And now we'll have a quick look at the animation describing this behavior. So we can first off see that we need to determine the form of the functional relationship between the interacting conditions, being bending moment equals load times distance. Furthermore, the load is equal to the constant, which is load per unit over distance times distance. Thus, we need to identify which dimension is changing with respect to another dimension and determine the independent variable. Therefore, in our triangular distributed loading case, the constant changes linearly with distance, or load equals constant distance times distance. Write differential df as a product of fx and an infinitely small change in the independent variable x. Substituting this back into our equation shows this. After we have calculated this, we integrate both sides of the function from some value x equals a to x equals b to calculate the net change in the dependent dimension f. Looking at this in a general solution, we can see the equations on the right hand side and the steps to finding these on the left. Just a general overview. Furthermore, in real-life applications, we can see an overhanging cantilever beam as a structure of the house. Down below, we can see a schematic diagram equating something similar to this overhanging cantilever beam, with the problem asking, use integration method to determine the values of slope and deflection at 2 meters from the free end of the cantilever due to the imposed load as shown in this figure. Having an in-depth look at this, equation 1 using Michelle's method can be found. Integrating equation 1, we find equation 2 with C1. To find C1, we apply the boundary condition of slope at x equals 4 and dy over dx equals 0. C1 thus equals 33.33, making equation 3. We integrate this to make equation 4. Now C2 is found when we apply the boundary condition for deflection, because the support at D is fixed and rigid. Therefore, at x equals 4, y equals 0. Substituting these values in, C2 thus equals minus 98.5, and dy over dx equals 28.66 over EI, and y equals minus 34.66 over EI. We use the moment of inertia calculated for the value of moment inertia for the T-beam section, equating this number. EI is a fixed number, making 727.52 kilonewtons meters squared, dy over dx equaling 0.0394 radians, and y equaling minus 0.47 meters, thus making a deflection of a negative bending moment. Thank you for your time.